Today we are going to be working with the Antoine equation. We are going to work with a set of data that is predefined. We will use Excel solver to estimate coefficients for the Antoine equation, and then we will do a multilinear regression using Python in Google's collaboratory software. So over here we have some experimental data. We have temperature in one column, and we have our data, our output, the pressure in pascals, over here in this other column. Now, using Excel, what our goal is going to be is to use Excel to give us the three Antoine coefficients, A, B, and C. And what I'm going to do is I'm going to define this little range here. Here, create from selection. And so we can create names for A, B, and C in the left column, which is this column right here. And we can define these letters so that it's easier to work with later on. Okay. So now these are going to be A, B, and C. There we go. Now our goal here is we want to find the model. We want to model this data. So I'm going to add a new column here for the data model using the Antoine equation. Now, the Antoine equation, if we look it up really quick, let me open up a new window. The Antoine equation is this equation right here. Log base 10 of the pressure is equal to A minus B over C plus T. And so essentially what we're going to be doing to model the pressure is we're going to put this expression to the 10th power to get the pressure alone by itself. So we can go ahead and do that in Excel. So we're going to say this is equal to 10, rather this, 10 to the A over, A minus, make sure I'm using the right thing, minus B over this temperature plus our C value. And right now, since we have no coefficients, no guesses, right now our P model is just going to show up as 1. But if we put initial guesses in these columns, so let's say our A is like 6. Oh boy, we're really starting to divulge pretty hard. But let's just put in the rest. Let's say A is 6, B is 10, and C is something like 4. Again, you see that this model really is not working with these coefficients. So that's because these are just random guesses for the coefficients we have right now. So in order to make this model match our data more cleanly, we can use Excel solver, which is this function here, to make a guess for our coefficients. Now the way we can force Excel using this solver function here, the way we can force Excel to give us a good fit for our model is to minimize the sum of the squared differences. And I'll show you what I mean in just a minute. So let me add a couple more columns here. Maybe just one for now. So I'm going to go ahead and complete this. As you can see, now we have completed the rest of the really bad model that we have based off of these guesses. And I'm going to find the difference between the data and the model. And so that's just going to look like this minus this, right? Complete that. Now, the issue is that if we were to use solver, it's going to make guesses, and some of those guesses might make our error positive, meaning that our model is less than our data, or it might be negative, meaning that our model is greater than our data. So to make sure that we are adding up errors, what we can do is make this a squared of the error. Because when we square a negative number, we get a positive number. And of course, if we square a positive number, we get a positive number. So we'll just square this. And we'll update. And now, what we want to do is we want to minimize the sum of the squared errors. So if we have something like sum squared error, something like that, this is just equal to the sum of this column right here. Oh, I'll just highlight them. Now we have a target cell. Now, what we can do with our newly made target cell is we'll now go into Excel Solver. And what Solver basically does, it's a solver that uses iteration to find the best possible solution based on the criteria that you give it. So now we have our objective, which is our sum of squared errors. And the only cells that we want to change are going to be these three cells here, A, B, and C. We're going to change the values of these coefficients to find the model that gives us the least amount of error. So I think we don't need that. Make sure that we want to minimize that error here, and let's hit solve. Now we look at the sum squared error and we see it, and we see that it's this huge number, and we think, oh well, maybe that means that our solution isn't very good. But actually, we take a look at the differences here, and we see that as we get higher and higher up into maybe around here, this is a very usable model. Our values are actually very close together. However, we see that in these earlier, maybe up until about here, in these first 5 or 6 cells, we see that our model drastically varies from our data. But in the end, we do have 3 coefficients that Excel tells us is the best solution for minimizing this error and minimizing the difference between our model and the data. Now, before we get into coding anything in Python, first we want to look at the Antoine equation once more. So if we remember the Antoine equation, log base 10 of the pressure is equal to A minus B over T plus C, right? Put this better. Now, when we look at doing a multilinear regression, we look at what is in our design matrix. So let's say we have some design matrix here, we have our coefficient matrix here, and we have just like some matrix of values that I'll call Y for now. Now say we have some polynomial, right? Let's just write a random polynomial. We'll say ax cubed plus bx squared plus cx equals y. The way that we structure our design matrices here is we look at, all right, so I have a bunch of x values. So we have an x1 cubed, an x2 cubed, dot, 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 to an xn cubed. And then same goes for your x1 squared, same goes for your random x. You know, you go all the way down to your nth term squared, your nth term to the first. And then what you have here is your A, B, C, D, or not your D, we only have A, B, C here. A, B, C. Your unknown coefficients for which you are doing a multilinear regression. And then you have your value of y. So your y1, your y2, your y3, which you know is from the data. So you have your inputs that you know, that you control. You have your outputs, which is a function of your inputs or can be decided from your experimental data. Well, what we have here with the Antoine equation, well, we see that we have log base 10p. This in itself doesn't give us any problem. What does give us a problem, though, is that t is jumbled up in this entire expression. So what we want to do is we want to manipulate this Antoine equation. Let me get rid of this here. We want to manipulate the Antoine equation to where we have t on one side and a whole bunch of calculables on the other. So that's kind of what we're going to do. So the first step is I look here and I find that I have a common denominator that I can multiply over. So that'll look like this equals a times t plus c minus b over t plus c. Essentially, we're multiplying the top and bottom of this value here by t plus c, and then we are subtracting them as is follows by the Antoine equation. Now the next thing we're probably going to do here is we'll multiply both sides by this denominator, and I'm also going to do the distribution in this step 2 so that we get somewhere close to our final to a final product of sorts. So let's go. We have t times log 10p plus c log 10p is equal to, and let's just multiply this out while we're at it. So we have at plus ac minus b. Now look at what we've done here. T log p, we know that. We know our t's, we know our p's. This is a value that we know. So essentially, this is going to go into our y matrix, our values matrix that we had before. And what we have here now are just a bunch of things that can be calculated. We have a c log p. Well, let's toss this onto the other side. Why don't we do that? So t log p, we'll put this on one side because this is something we know, is equal to, let's go, at minus c log 10p plus, and I'm going to keep ac minus b as its own term. Let's just go ac minus b. Now, the next thing that might feel natural for us to do, let's start making our design matrix, our values matrix, and our coefficient matrix. So we'll start with this side. We'll create our matrix for t log 10p. So what that's going to look like is something like this. So we have t1 log 10 p1, then we have a t2 log 10 p2, all the way down until we have some nth temperature log 10, some nth pressure. Here's our values matrix. Now, when we look at variables that are in question, that's t and p. The rest are coefficients. So essentially, when we write down our design matrix, let's go like this. We don't really worry about these coefficients because that'll come in the coefficient matrix. So this will come like t1, t2, yada yada, some nth term temperature, some p1, p2, some nth term pressure, and a column of ones because this last term, ac minus b, does not have a t or a p. It doesn't have any of the variables that we really worry about. So in our coefficient matrix, that's where the coefficients will show up. So our coefficients are going to be a, c, and ac minus b. And this is very useful because if we know AC and AC minus B, we can calculate B. So we can find A, B, and C just using this setup right here. So now we're in a brand new collaboratory notebook. I've gone ahead and I've imported some libraries and tools that'll make life a little easier later on. And I've actually also gone ahead and I've imported the water vapor pressure that we had actually used for the Excel solver as well. That's that temperature and pressure data that we had. And so if the way that we can import it into our notebook and start being able to use that data to do our regression is something called the gen from text function, gen from text. And what you have to do here is we'll put in our file name. So that was water vapor pressure .csv. That's a comma separated values. So that means that our delineator or delimiter, our delimiter is just a comma. And there you go. It pulls out the data that we will need to move forward with the coding and whatnot. Now, I'm going to save this array to just something called, we'll just call it variable data. So now it's just saved into that variable. And if you remember, the first column is for our temperatures and our second column was for our pressures. And since we want to work with these independently, I'm also going to unpack these into other variables, T and P. And the way I'll do that is we'll go data, and then this is basically saying that if we put a colon here, that's saying everything in the first column will be the temperature. So we're looking at this data array. This column operator or colon operator means everything in the column that you specify, and that column we're specifying is column 0, which is technically column 1 because Python goes from 0 onwards. It goes 0, 1, 2, so on when you're counting columns. And so let's take a look. Is it saved properly? Yeah, perfect. So let's do the same thing for the pressure. Toss that in there. Data bracket colon 1, not semicolon, a colon. And now we also have our pressures there too. So now we have all the data that we need to work with. We can start coding in our design matrices and go forth from there. So we're going to create our design matrix A using this NP concatenate feature. And if we go back to our design matrix, we see this should be a minus log 10. I just realized that. This should be different. How do I... move this all over a little bit? Nope. Gosh. Yeah, let's just move this over a little bit. And this should be, since it's tied to this log 10 operator, it should be a minus log 10p. In fact, I should probably move this entire thing over. Here we go. So now we got minus log 10, minus log 10, minus log 10 of the pressures. So now that's good. So our design matrix is, the first column is our temperatures. The second column is the negative log 10 of the pressures. And then we have a column of ones, the same length as the length of the other column. So go ahead and code this out. So our first column is our temperatures, right? Our second column, we're going to use minus np.log 10, np.log 10 of the pressures. And then we're going to have an np ones underscore like, And this is basically going to add a column of ones that is the same length as the column you specify. So let's specify the temperature, because the temperature and the pressure, it's got the same length. Shouldn't really matter. And if you look at this now, we have exactly what we need. We have our temperature in the first column. We have the negative log 10 of the pressures, and just a column of ones that we can work with. So now let's also go ahead and we'll throw in our values matrix here that we had. Where's my whiteboard? Yeah, we have our values matrix. That's our T log P. So we'll go ahead and we'll assign this other matrix. We'll call it T log P. Pretty straightforward. And T log P is going to be our temperature array times np.log10 of the pressures. Now T log P, yeah, that looks about right too. So now we can use our solving features. So now np.linalg solve. And this is what's going to give us our coefficient matrix. So our left-hand side is going to look something like this, where we transpose our design matrix. So that's just going to be a.t, do a matrix multiplication with our T log P, or we'll leave it like this. We'll go transpose times the design matrix, and our second is going to be our transpose times the T log P matrix. And now we have our 3 values for a coefficient matrix. Now remember, the first value is A, the second value is C, but this third value isn't B, it's AC minus B. So in order to find out what B is, we can rearrange. So really quickly, just do some rearranging on the side. If we want to find out what B is, AC minus B equals some value. If we want to find out what AC minus B is, if they're equal to each other, or not equal to each other, they're equal to some value. I'll call it X, why not? Then we have this value, and we're going to basically swap this, AC minus that, equal to B. So that's what we can also do in Python to find what our B value is. So now let's store values, right? So our first value was A. I actually don't love using A, so maybe a lowercase a. Maybe that should work. B, and then AC minus B, underscore B, that should work. Equals that. Because since we're using A for our matrix and we're also using A for our coefficient, I don't want to mix those two up, right? So let's store that, unpack that. And now to find B, or sorry, this should be C. B is just going to be equal to our A times C minus our AC minus B. So AC underscore B. And if we do that and find B, there we go. We have a value for B now. And so let's look at all 3 of them. Let's go A, B, C. We now have 3 values for our Antoine coefficient. Now, what I quickly want to brush on here is I've tossed in our values from our Python notebook here. Toss these values into our old Excel sheet. And we see now that this data matches much, much, much better. Actually, in between, I also found that I made a little typo here, but that should be fixed now. But yeah, we see that this fits much better. And instead of looking at a sum of squared differences, I think what probably makes a bit more sense to look at is maybe just a percent error. So why don't we just do that? So let's do an absolute difference between this and this, divided by the experimental. And you already see that this is very, very, very good fit. This percent error is nearly negligible in almost all of these cells. So Python did a really good job at finding a good model for us using the multilinear regression. And we can also show that by plotting out the old data and the new data in Python. So let's code this in Python really quick. So I'm going to go fig equals make subplots. Boom. This is going to create our plot that we're going to be graphing our model and our Antoine model, or our data and our Antoine model in. So first, let's add a scatter. So fig.add scatter. And this is going to be our data. So our data is on our x-axis. That's just going to be our temperature array. Our y-axis is going to be our pressure array. Since we're plotting these, and these are data points, we're going to set our mode equal to markers. And I'm just going to give this a name. Name equals, and we'll call this data. Right? So now we see that we have our temperature on our x-axis, our pressures on our y-axis. But a quick little thing that I'm probably going to do here, I'm probably going to switch my y-axis to a logarithmic, because you see that we're dealing with an exponential on a very, very large magnitude here. So let's just go ahead and I'll go fig.update y-axis, and we're going to switch this to a log plot. And now you see that we're in a logarithmic scale. This is just easier to read, and it'll help us, you know, if we're ever presenting information, it'll help us properly employ our data trend. Right? So next thing I'm going to do is, although we have a set of temperatures that aligns with this array, for the model we want to use interpolation. Since we have an equation, the Antoine equation, that we base our model off of, we can use more data points inside our range to give us a very accurate model. Otherwise, you are jumping from, say, 300 Kelvin to 330 Kelvin. Well, what happens between 300 and 330? It's not just a straight line. It's going to follow that curvature. So what we're going to do, I'm going to set up a temperature model. And what I'm going to do is I'm going to use the np.linspace function. And what I'm going to do, as Gemini is already kind of guessing, I'm going to take the minimum of my array and use that as a starting point. I'll take the maximum of my array, use that as my ending point, and let's say we want 100 data points in between. Now, when we look at it, we have a lot more data points for which we can analyze the pressure, which is good because we want a very accurate model. So let's use that, and we'll add another scatter here, so kind of the same thing. Add scatter, and our x this time is going to be our t model, and our y is going to follow our Antoine equation. So y is going to be equal to 10 to the a minus b over, in parentheses, t model plus c. And we have a, b, and c from our multilinear regression, as you may remember. We'll set the mode equal to lines, because now we are plotting a model. We want to see how the model interacts with the data that we have, and how we can interpolate the data looking at our graph. And we'll name this Antoine. Why not? Antoine. See, now we have a very nice looking curve. And as we saw back in our Excel spreadsheet, there is a very good level of agreement between our data and our model. The error is minimized using that linear regression we did earlier. And that is how we can plot our data and our model using Python.